Hello there, Mr. Sutton here, bringing you the AB Calculus 512 Extra Practice number 2 solutions on FTC free response practice. For this free response problem, we've got this graph of f up here, and our first task, given the function g, which is the integral from -4 to x of f of t dt, our first task given this function is just to find g of -1 and also g prime and g double prime of -1. Or state that these don't exist, because that's an option too. So for g of -1, we're just doing the integral from -4 to -1 of f of t dt. So that's asking for this area under the curve between -4 and -1. That's going to be a trapezoid, and because this is under the x-axis and we're going from left to right, this is going to be considered negative area. So we're going to have negative, and now here's our trapezoid area. We have a base of 3 plus a base of 2, all divided by 2, times a height of, let's see, this is going to be a distance of 3 here. So -3 minus 2 over 2 times 3. This is -5 over 2 times 3, which is -15 over 2 if you wanted to simplify it. Next, let's talk about g prime of -1. So for this one, if you take g prime of x in general, using our fundamental theorem, that's just going to be f of x. You're just putting this upper limit in for the dummy variable. So g prime of -1 is really just f of -1, which if we actually look on the graph here of f of -1, we have a point right there, that's going to be -2. And now finally, g prime of -1, that's going to be the slope at -1 on the graph of f, because g double prime is what we're finding here. That's going to be f prime of -1. So f prime, let's see here, slope at -1 on the f graph to find g double prime. Well, we have a corner there, so this actually does not exist. For this part of the problem, for the function g defined in part A, they want us to find the x-coordinate of each point of inflection on the graph of g on the interval from -4 to 3. So the key here, if you're looking for points of inflection, there's two ways you can do it. One is figuring out where g double prime changes sign. The other, which might be a little easier on this one, is to figure out where g prime reverses direction, changes from increasing to decreasing or decreasing to increasing. So here again is the g function from part A. Now the key on this, since we're talking about g prime, is recognizing because of the FTC here, g prime of x equals f of x. We didn't actually write that explicitly yet, so let's write it now. So f of x, also known as g prime of x, changes from increasing to decreasing, reverses directions, at x equals 1. And that's the only place that we're reversing directions. So therefore, that means that g has a point of inflection at x equals 1. On this part of the problem, this one's a little bit tricky. They're giving us the h function, which is the integral from x to 3 of f of t dt. So kind of like the g function, but a little bit different with those limits of integration. Notice that the x now is in the lower limit of integration. Anyway, they want us to find all x values between -4 and 3, where h of x equals 0. Okay, so we're basically asking for a c value such that the areas on the interval from c to 3 are going to cancel out. The negative and positive areas that you would find by basically taking this integral by looking under the graph of f. So let's start with the easiest one. If I plug in the x value 3, well, this would give us the integral from 3 to 3, which no matter what is going on with f, that is going to be an empty integral since you're not really acquiring any area one way or another. So 3 is definitely going to be an answer here. So just starting here, let's work backwards. So we have this negative area from 2 to 3. But if we go a little further back to go from 1 to 3, then this positive area and this negative area, which are exactly the same, are going to cancel out. So x equals 1 is another one where your integral is going to give you 0. And then if we go a little further back, we have another positive area that we've acquired. But going further back, this negative area cancels out this positive area. So if you go from -1 to 3, that also would give you a value of 0. And if you go back further, it's all negative area. No way to cancel out this stuff at this point. So 3, 1, and negative 1 then are our final answers. For this last problem part, we're using the function h again from part C. So let me just rewrite that. There we go. And we want to find intervals where h is decreasing. So for this one, we're essentially asking, where is h prime negative? So we need to figure out what h prime of x looks like. Now, before you go ahead and just take the derivative of both sides, one key ingredient here that you might miss out on is that this x is in the lower limit of integration. So when you're using the FTC and just plugging the x in for the dummy variable, you have to remember that's when the x was in the upper limit of integration. But the way these things work out, you can't do the same thing if x is down here. That's okay, though. We can do one little trick here to switch things around. If I want to write this as the integral from 3 to x instead of x to 3, I can do that by just negating this integral. This is just one of our integral properties. When you switch the limits of integration, you just get the opposite version of what you started with. So now, given this situation, I can write that h prime of x equals negative f of x. And when I'm asking where h prime is negative, well, I'm asking where negative f of x is negative. And because we've got this sign reversal going on, negative f of x is going to be negative wherever f of x itself is positive, because you'll have a positive times a negative. So where's f of x itself positive? Well, there's really only one interval from 0 to 2. That's the only place we're above the x-axis. Everywhere else we're below. So this is all going to come out negative, less than 0, on the interval from 0 to 2. Therefore, that means that h is decreasing on the interval from 0 to 2. On this free response problem, the rate at which water is leaking from a container is modeled by a twice differentiable function r, and r of t is gallons per hour. And let's see here, they're giving us some values for r of t between 0 and 1 in this table up here. So the first task is just to use the data in that table to figure out an approximation for r prime of 1/2. So whenever you want to approximate an IROC, an instantaneous rate of change, really the only way to do that is with an average rate of change that involves the value that you're plugging into the derivative. So to approximate this particular value, I want to find the average rate of change over an interval here for r that involves 1/2. So looking at my table here, 1/2, that is between 1/3 and 2/3. So if I find the average rate of change between 1/3 and 2/3, that'll give me an approximation of this r prime right here. So I'm going to do AROC then. I'm going to say r prime of 1/2 is approximately equal to r of 2/3 minus r of 1/3 over 2/3 minus 1/3. So this is a good setup, and again, notice I put approximately equals here because they're asking for an approximation. If I write equals here, I've already written something incorrect because this definitely does not necessarily equal my derivative. All right, so moving forward, I'm not quite done because what is r of 2/3? Well, in the table here, r of 2/3 is 5. So we have 5 minus r of 1/3, which is 8. And once I've written all of this out, I'm actually done as long as I put units on the end. But if you wanted to simplify it, this is going to be negative 3 over 1/3, which you could reduce to negative 9. But now the important question here is, what are the units? Well, you just basically took the derivative of something that already had units of gallons per hour. Every time you take the derivative with respect to time, you're dividing by another time unit. So this is now going to be gallons per hour, or gallons per hour squared. For this part of the problem, they're asking us to use a left Riemann sum with 3 subintervals with the table to approximate integral from 0 to 1 of r of t dt. Okay, so we're going to say that this integral is approximately equal to the following. And now I'm going to have 3 base times height rectangle areas going on. Now the bases are just going to be these hourly distances here. So they're all going to have a base of 1/3 because it's the same distance, it's the same increments each time. The heights are going to be, well, we have a choice between a left and a right rectangle height here based off of these r of t values. Since this is a left Riemann sum, we're always going to go with the left height of each rectangle. So the first rectangle, we're going to have a base of 1/3 times a height of 11. After that, we have a base of 1/3 times a height of 8, and a base of 1/3 times a height of 5. And if you put units on the end, you're actually done with the problem because this is all numbers here. But if you wanted to simplify it, we could yank a 1/3 out of all that and have 11 plus 8 plus 5 in a parentheses. And then let's see here, 11 plus 8 is 19, plus 5 is 24. So we have a third of 24, which is just going to be 8. And now what's the units? Well, whenever you integrate something, you're basically multiplying it by a time unit. That's what this times dt really means. So if you're starting with gallons per hour times hours, that's going to give you gallons. For this problem part, they want us to use the data in the table to evaluate integral from 0 to 1/3 of r prime of t dt. So this one actually isn't so bad because the antiderivative of r prime is just r. So this is really just evaluating r of t from 0 to 1/3, which basically just means we're doing r of 1/3 minus r of 0. Well, what is r of 1/3? We can find that directly in the table. They told us that that was 8. What's r of 0? Well, that's 11. So this is just 8 minus 11. And in case you're wondering here, the units on this is just going to be gallons per hour because it's basically the same units as r of t. So -3 gallons per hour. On this problem, they're giving us this weird-looking sum here that's a right Riemann sum with n intervals of equal length. The limit of this sum as n goes to infinity can be interpreted as a definite integral. So they've basically given us the infinite integral Riemann, or the infinite rectangle Riemann sum version of a definite integral. They just want us to put this in definite integral form. So the function involved here is just the r function. This is basically an integral of the r function. We want to put this in the form of integral from a to b of r of x dx. Really, what we need to figure out is just the a and the b value, the limits of integration. Everything else is kind of rolled into writing just r of x dx here. So the a value, that's typically whatever's being added to the k and the n term here. So this 1/4 inside, that's going to be our a value, our lower limit of integration. To get the b value, we need to figure out the interval length. Now the interval length is always whatever you're dividing n by, in this term out here. But this is kind of weird. We have 1 over 2n. You could really think of this as being 1/2 divided by n, in which case your interval length is going to be 1/2. So that means there's a distance of 1/2 between 1/4 and the b value. So to find the b value, the upper limit of integration, we just have to add that interval length of 1/2 to 1/4. So this is 1/2 plus, or 1/4 rather, plus 2/4. That gives us a b value of 3/4. So going back and rewriting this, we can write this as the integral from 1/2, or rather 1/4, my fractions are getting mixed up, from 1/4 to 3/4 of r of x dx. There we go.